Okay, so let's do your homework questions real quick.
Okay.
So starting with questions from exercises 1. Go through them chronologically. What's the first one you have questions with?
6.
6, that's the first one for him. Anyone have a question before 6?
I think 1C. I didn't know how to justify that.
So 1C is false.
No.
My example is square root of 2 minus square root of 2 is rational. So I'm guessing it said something like the difference of irrationals is always irrational. No?
No, it's the sum of irrational numbers is irrational.
Oh, okay. So 6 or square root of 2 plus negative square root of 2.
My exact example.
Okay.
That's actually, if that's not the exact problem, it's something like that was exactly one of the things I got stuck on one of my finals. They said something like, prove that the sum of irrationals is irrational. And I spent, so it's a time final, and I spent like more than half my time trying to do that stupid proof until I finally realized it's not true. Wrote a counterexample, went on my way. So mad.
Yeah, that'd be frustrating.
Yeah, it was annoying. Next.
I had a question on 3.
On 3. So this one's a proof by induction, proving I squared is equal to n times n plus 1 times 2n plus 1 over 6. Right?
Mm-hmm.
Okay. So proof that the sum from I equals 0 to n,
It'd be from 1.
or I guess we could start from 1, doesn't matter, of I squared is equal to n times n plus 1 times 2n plus 1 all over 6, right? So how do we set this up? Let's do it real fast. 1, let A equal the set of all natural numbers, all n and n, such that n makes this true. I don't want to rewrite out that statement. You understand what A is?
Yeah.
Okay, first thing we gotta do, well, we're proving A is inductive. How do we do that? We prove that 1 is an A, and then we prove that if K is an A, K plus 1 is an A. So next would be something like base case, n equal 1 gives, we'll write it out, the sum from I equals 1 to 1 of 1 squared is equal to 1 is equal to 1 times 2 times 3 all over 6, which implies 1 is in A. Doing it real quick and messy, right? So 3, assume K is in A. So if K is in A, then that means the statement is true for K. Then the sum from I equals 1 to K of I squared is equal to K times K plus 1 times 2K plus 1 all over 6. Now when I'm doing a proof by induction, I personally like to go to the side and try to see where I'm trying to get. I'm trying to show that K being an A implies K plus 1's an A. I know K plus 1's an A when I know that the sum up to K plus 1 equals when I plug in K plus 1 for K into this, right? So I'm trying to get that the sum of K plus 1 is equal to K plus 1 times K plus 2 times 2K plus 3 over 6. That's what you get when you plug in K plus 1 in for this half. So I'm trying to show that the sum from up to K plus 1, I equals 1 of I squared is equal to that. Once I've shown that, we're good. So I'm going to take this equation and I'm going to add K plus 1 squared to both sides. So 5, then the sum up to K plus 1 from I equals 1 of I squared is equal to K times K plus 1 times 2K plus 1 all over 6 plus K plus 1 squared. Any questions on that step?
Oh, that's where I went wrong then. I did square the K plus 1.
Oh, right. So I need to add the same thing to both sides.
Right,
And then you just do the algebra to manipulate this to look like this,
okay.
and you're done. Do you need to see that? Anyone raise your hand if you want to see that?
Okay, but wait, why do you add k plus 1 squared?
So I have, when I go from this to this, then I added k plus 1 squared to both sides.
Because I is squared.
Yeah, because the I is squared. What is this sum short for? This is short for 1 squared plus 2 squared plus 3 squared plus 4 squared all the way up to k plus 1 squared.
Oh.
This is 1 squared plus 2 squared plus 3 squared all the way up to k squared. So to get from this to this, I need to add a k plus 1 squared.
Okay.
And if what I do to one side, I do to the other side. And then the algebra here is just the algebra here. I think we can do that. We're good? Okay, and you know how to continue that proof. Or do you want to see the rest?
No,
Okay. So next question.
was number 5?
Number 5. Number 5, the cubed one.
This is a big beaver.
Okay, so this is where you're supposed to use what we've already proved and not reinvent the wheel, so to speak. So we're proving that the sum cubed is equal to the sum from I equals 1 to n of I, this whole sum squared, correct?
Yeah.
Now, we already know what this sum is from a previous proof.
Yep.
It's n times n plus 1 over 2, right? So this is the same thing as proving that it's equal to n times n plus 1 over 2 squared, or in other words, proving that it's equal to n squared times n plus 1 squared over 4. So I'm proving that this is equal to this, and I'm done.
Okay.
So that's the tricky part to this, the tricky as in the part that's different from other standard proofs by induction. Outside of that is the standard proof by induction. So base case, we won't write out all the sets and everything formally, we'll just go high level. Base case, is it true for 1? Well, 1 cubed is equal to 1 squared times 2 squared over 4. Okay, it's true for 1. Assume it's true for k, so assume that the sum from I equals 1 to k of I cubed is equal to k squared times k plus 1 squared all over 4. Where are we trying to get? We're trying to get that the sum from I equals 1 to k plus 1 of I cubed is equal to k plus 1 squared times k plus 2 squared all over 4. Once we've shown this, we're done, right?
Yes.
Okay, so how do I get from this to this? What do I need to add?
Okay, this one cubes both
I
sides.
need to add a k plus 1 cubed to both sides. So then, this sum from I equals 1 to k plus 1 of I cubed is equal to k squared times k plus 1 squared all over 4 plus k plus 1 cubed. So did you just get stuck in the algebra manipulating this to this?
What's up? Some hairy algebra.
Let's just continue it then. Okay, so we need to get a common denominator, times this by 4, times this thing top and bottom by 4, and then I'm going to factor out the k plus 1 squared. So we're going to get k plus 1, let me know if this is too many steps in one, times k squared plus 4 k plus 1 all over 4.
Yes.
I factored out a k plus 1 squared from both these terms. That's right here. And I multiplied this term top and bottom by 4. So it's still right here.
Why did you factor out a k plus 1 squared? Oh, because you need it.
Look at what I'm getting
Okay.
at.
So you did it the easy way. I totally did it the long way. Like I shouldn't have done that.
So So is there any questions going from here to here? We're good with that? Okay, and now I just need to rewrite this as k plus 2 squared. So this is the same thing as k plus 1 squared times k squared plus 4k plus 4. If we want to do this in 2 steps, k squared plus 4k plus 4 all over 4. And then finally, this can be factored into k plus 2 squared. So rewrite this as k plus 2 squared. We have that, therefore k plus 1's in A, and da-da-da-da-da-da. I think you know how to take it from there.
Yeah.
So we're good on that one? Yeah, it's good to get comfortable with these proof by inductions because at the start of this class you feel like those are kind of a pain. Once you get in the middle of the class, anytime you can do a proof by induction, you're like, oh, thank goodness.
Honestly.
A standard way of doing a proof. I don't have to think about it. I just do the base case, and you just have to do the algebra, and it just comes out, and you're like, oh, lovely.
I'm glad we did like 100 of these last year.
Yeah, you're at the disadvantage of not already doing discrete math. You'll see when we come across this in discrete math, and then when that comes up, this is going to be easy because this is the hardest proof by induction you do in discrete math.
Yeah.
So, that's not true. The binomial theorem, which hopefully we can cover today. Any other questions on homework?
Yeah.
Yes.
So,
So I had a question. Did you have a question on 6? Or
kind of.
Seven.
I did it, but like I said, I'm really not sure.
So, what one was it on?
AME?
If I did A right, then I did B right. But if I did A wrong.
Alright, so let's just cover A really quick. So, it's proving that the sum of two naturals is a natural, right?
Yeah. Should feels like it shouldn't be this hard.
So, I'm going to phrase this to try and help hint at how to do the proof. Proof. If M is in N, then N plus M is in N for all N in N. So if M is a natural number, then adding a natural number to it is always produces a natural number. Okay? So I'm going to prove that when you add 1 to it, it is. Assume that when you add k to it, it is. Therefore, when you add k plus 1 to it, it is. And we're done.
Okay, so to prove something is a natural number, it's just you prove that by induction,
So
right?
what we do is we say let A be the set of all natural numbers that make it true. And then if A is inductive, then it is a set of natural numbers. So we define A so that A is a subset of the natural numbers. That's how we define it. Then we show that A itself is inductive. And remember that the natural numbers are a subset of every inductive set. So by showing A is inductive, then we show that the natural numbers are a subset of A. And if A is a subset of the natural numbers and the natural numbers are a subset of A, then they're the same set. So we make A the set of all the natural numbers n that make this equation true. Let's do a proof by induction. This time let's be explicit with all our steps so that we can see all the thinking behind the scenes of exactly what's going on. So let's not do this one quick and dirty. Let's do it right. 1. Let A equal the set of all the natural numbers in n. Sorry, we actually need to start by let m be a natural number. Remember, we have an if-then here. So we need to assume our antecedent and try and find a color that isn't dying. 1. Let m be a natural number. 2. Let A equal the set of all the natural numbers, all n in n, such that, oops, forgot we're doing this, such that with the colon, such that m plus n is a natural number. Now notice that by definition of A is a subset of the natural numbers. Because we said A is the natural numbers that make this equation true.
Right.
So the only thing in A is natural numbers, so we know by definition of A it's a subset of n. Our goal from here on out is to prove that A is inductive. If A is inductive and it's a subset of the natural numbers, it is the natural numbers. So that's our goal from here on out, show A is inductive. How do you show a set's inductive? You show 1's in it, and you show that if K is in it, then K plus 1 is in it.
So here's
That's what it means to be inductive. It satisfies those two properties.
one of the issues I have. If 0 is not a natural number, then the smallest number in that set is 2.
1. Why are you skipping 1?
Because 1 plus 1 is 2.
M is some natural number. Doesn't matter what it is. Some natural number out there. When I add 1 to it, is it still a natural number? N is a set of all the natural numbers, such that when I add it to whatever that is, it's a natural number.
I did.
That's why, yeah, I told you that big hint in how I'm setting up this if-then on how to solve the problem.
I set it up a different way, so that's probably why.
Yeah, we didn't hammer this home. I didn't bother because you two had already taken discrete math and she was going to get discrete math. But anytime you're doing a proof, rephrase it as an if-then statement. Every proof you're required to do can be phrased in terms of an if this, then this, and it will help you try and anticipate what you need to assume to prove it.
I get that. What I did is I had a Q, that n plus m was Q, and I was showing that Q is in the natural numbers.
So, but see how your brain already would say you can't do that inductively, because you're saying if m and n are natural numbers, then Q is a natural number. What do you induct on? Q?
Yeah.
So when the sum is equal to 1, then it works. When the sum's equal to 2, then it works. When the sum's equal to 3, then it works. You have to assume it's true to do that.
No, you don't.
Yes, you do.
Yeah.
There's not a sum of two natural numbers that produces 1.
That's my point.
Okay, now I see why you're stuck. And now you see why you couldn't do it that way.
Yeah.
So this is the way that you have to do it.
So what I ended up just doing was
I don't know that have to, but this
hey,
works.
I'm going to say we're going to let it equal to that or let it equal to 1.
So that's actually,
Prove it.
we'll see a strategy where we need to do that. That's in the, when you subtract, then you need to have a thought process kind of like that.
So
Anyways.
did I just do it totally wrong? I need to redo it.
Yeah, the way that you're doing the logic doesn't follow. Okay. So anyways, let A be the set of all the natural numbers that you can add to M and still get a natural number. 3. Observe that M plus 1 is in N since N is inductive. Right? We know that the natural numbers are inductive, which means anytime M is a natural number, M plus 1 is a natural number. That's the definition of inductive. 4, therefore 1 is in A. So we showed 1's in A. Now we need to show if K is in A, K plus 1's in A. Right?
Okay, I'm so confused. M plus 1 is in N.
So remember, the natural numbers are inductive. We proved that earlier.
What is N? Or what is, what is
sorry.
1?
This is
What
the
is
set of
1?
all natural numbers.
1 right there. It's a natural number, correct?
Oh, sorry. Maybe I need parentheses here.
It's a natural number though, right?
Yeah, 1's a natural number.
And we're saying M is a natural number.
Uh-huh.
Therefore, we just kind of proved that.
Well, no, we proved that it's true for 1. I proved that a natural number plus 1 is a natural number. Now I need to show that a natural number plus any natural number is a natural number. You see the difference?
Yes, sorry, okay, continue.
So, by definition of n being inductive, anytime m is a natural number, m plus 1 is a natural number. That's in the definition of inductive. N is an inductive set. So therefore, that's a property that n satisfies.
Right.
Anytime k is in there, k plus 1 is in there. Anytime m is in there, m plus 1 is in there. Okay, so, and remember, what's A? A is a set of all natural numbers that I can add to m and still get a natural number. I just barely showed I can add 1 to m and still get a natural number. Therefore, 1 is in A. So we showed that 1's in A. Now we need to show that if k is in A, k plus 1's in A. Therefore, A is inductive. Therefore, it's a subset of natural numbers. Therefore, it is a natural numbers. That's big thinking where we're going. So, 5. Assume that k is in A. Comma, and observe that k, that m plus k is in the naturals. Perfect. That's what it means for k to be in A.
Mhm.
K to be in A means that m plus k is a natural.
Tricky.
6. Then m plus k plus 1 is a natural. How do I know that?
Because it's
By definition of it, we know that n is inductive.
Yeah.
Since n is inductive, any natural number plus 1 is in n. Therefore, n plus k plus 1 is in n. Or if we want to write that in a more helpful way, n plus k plus 1 is in n.
boom.
7.
Then A is equal to M.
Well, almost. Therefore, k plus 1 is in A. When I add k plus 1 to m, I got a natural number. Therefore, k plus 1 is in A. Therefore, every time k was in A, k plus 1 was in A. So,
Now there you go.
now we can say that they're inductive. Therefore, A is inductive. A is inductive. Which gives me that,
A equals M.
yeah, which gives me n's a subset of A, which gives me n is equal to A. Because I already knew up here that A was a subset of n, n's a subset of A, therefore they're the same set, therefore it's true for every natural number. Alright, so we just proved that the sum of any two natural numbers is a natural. And the proof that the product of any two natural numbers follows that exact pattern. It's a very similar type of thinking. Except for instead of the plus 1 here, you're referencing this proof. Sorry.
Well,
You'd use this proof to prove it for multiplication if you went to the proof. I think you'd see it. The trick for showing the plus 1 case, the 1 case, is to use this proof, and then you assume it's true for the k, and then you rewrite it with the plus 1, and you reference this proof again. The same way that this proof references n being inductive twice for our plus 1s, then timesing by 1 more references this proof twice. It's not that hard. I think I'm making it sound more complicated than it is.
okay. Can you
All right.
take a quick look at my A and show me the exact step where I went wrong? Because I feel like it's down.
Let m and n be natural numbers. Let x be the set of all q, such that m plus n is q, and m, n, and q are natural numbers, or q is equal to 1. The set of all q, where q is, you put your or in the wrong spot, where m plus n is equal to q, or q is 1, and m and n are natural numbers. And you put q and n over here. So it's a set of all q and n such that
And M.
q is a sum of two natural numbers, or q is equal to 1.
So I'd say Q, M, and N in the natural numbers such that
You put the q and n at the start. So you
not them.
do it like this for your q. The set of all q and n such that
Oh,
q is equal to the sum of two things, and those two things are natural numbers, or q is equal to 1.
okay.
So that's how you set that up so that it reads correctly. Note that 1 plus 1 is equal to 2, which gives 2 in n, so 2 is in x. Okay, 2 is in x. So already what you're trying to prove is that I can sum two natural numbers to produce every natural number starting at 2.
Yeah.
I'm not proving that the sum of any two natural numbers is a natural. I'm proving that by picking two natural numbers, I can get any natural I want. It's not the same thing. So for example, your proof never requires me to check 3 plus 4. I could do 1 plus 1 to get 2. I could do 1 plus 2 to get 3. I could do 1 plus 3 to get 4, etc. And I could generate all the natural numbers in x this way to show that x has every natural number and that we never handled this case.
Okay.
So you just proved that by summing naturals, I can produce any natural I want. You didn't prove that the sum of any two naturals is a natural. You see the difference in the logic there?
Yeah.
Yeah. Okay.
Okay, well,
And then part B is almost identical, right?
yeah.
Is that the multiplication one?
Yeah, I did it wrong.
Do we need to go through that one, or do you think you can do it now?
I guess we'll find out.
Yeah, it's definitely on the test, so be ready for that next week. Okay. What's next?
7.
And then
7, which, yeah.
7. So 7 was the minus one, right?
Yes.
Okay, let's see exactly what it's saying. Proof. If n is a natural where n is greater than 1, then n minus 1 is a natural, right?
Yes.
So, proof. If n is a natural such that n is greater than 1, comma, then n minus 1 is a natural. Okay. So 1, here's what we're going to do, something similar to what Levi was thinking. Let A be the set of all n such that let all natural numbers such that n is equal to 1 or n minus 1 is a natural.
Are we putting that equal to a variable?
Is that set A?
Oh, yeah. Let A equal that set. Sorry. Now, the only reason that we're going to do this n equal to 1 is because the statement obviously isn't true for 1, and we want to show that A is equal to the set of all natural numbers.
Right.
Now, you'll get this in discrete math, but for those of you in discrete math, you realize that sometimes when we do a proof by induction, we start at 2 instead of 1, or we start at 5 instead of 1. We show it's true from 2 onwards, or from 5 onwards. Behind the scenes, this is what we do so that we don't have to deal with those. So if you want to show that something's true from 3 onwards, we show the set containing 1, 2, or all the natural numbers that satisfy it is the natural numbers. And that way, that's how you handle it behind the scenes. But we don't explicitly mention that, and most times when you see a proof, they'll say base case and start at 3 or whatever. So typically when we prove this, I'll do it both ways. I'll show you doing it explicitly, and then we'll do base case starting at 2 and show you the kind of the fast hand way to do it, if that makes sense. All right.
Is there a way, like an interval notation for natural numbers? Like, you can say all the natural numbers from 1 to 500 without having to write them all out. Is that?
Yeah. 1, comma, 2, comma, dot, 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 comma, 500.
Okay.
That's how you write it.
Seems so. I don't know.
Well, the only time you write with that notation is if you're saying the pattern's obvious, you should be able to get it from this.
Yeah.
Yeah. So, observe that 1 is in A,
Right. By definition.
by definition, comma, and that 2 minus 1 equal to 1 implies 2 is in A. So we need to get to our base case where the statement starts being true. In this case, that's going to happen at 2.
Because it equals 1 or because it equals a natural number?
Basically, I need to show really quick that there is some number, namely 2, that satisfies this statement. Because on my assume case now, when I say assume k is a number in there greater than 1, the only way I can say assume k is a number in there greater than 1 is if I first thought there's a number in there greater than 1.
Right.
So there's at least 1,
Which is
right? So when I do my assume, 3, assume k in A such that k is greater than 1.
Oh, so that fixes it.
Right. That's why we have to do the 2 in there.
Right.
So that we can say, now grab something in there that's not 1. What does that mean?
K is positive.
Then,
Yeah, doing the positive proofs threw me so hard.
oh, when you're proving with the integers?
Yeah, because you couldn't say that they aren't negative.
So let's see. Showing that, assume that k is in A, what does that make k? K is a natural number such that when you minus 1 from it, it's still a natural number, right? So then, we have that k is in N, and k minus 1 is in N. It's a natural number that such that when you subtract 1 from it, it's a natural.
Because we showed that it's true for 2. Therefore, it could be true for any of them.
Well, so we showed it's true for 2, means that we're guaranteed that there is some element k in A such that k is greater than 1.
Right, so K could be 2.
So k could be 2, it could be anything.
Right.
But we can't assume that there's an element of a certain type in there until we prove that there's one.
Right, okay.
So, in other words, if I want to say, let P be an even prime, I can't do that until I show that there's at least one even prime. Then I can grab one of those. So I'm saying, here's something in A greater than 1. Now we can assume that there is some k in A such that k is greater than 1. That satisfies the statement. And we're going to show that anytime that's true, it's true for k plus 1 as well. Which then shows you intuitively, okay, that's how I get from 2 to 3, and 3 to 4, and 4 to 5, and 5 to 6. So proof by induction, we're always saying, it's true for some number, we find some natural number that it's true for, and then we show it's true from that number onwards. Therefore, it's true for every natural number starting here. That's what we always are doing in proof by induction. So anyways, so then k is in N, and k minus 1's in N. Then, k plus 1 is in N, and k equal to k plus 1 minus 1 is in N. How do I know that k plus 1's in N?
Because it's inductive.
N's inductive. And then how do I know that k plus 1 minus 1's in N? Because k was in N. So since k is in N, k is in N. And since k is in N, k plus 1's in N.
And k...
So k plus 1 being in N implies k plus 1 minus 1 is in N.
Okay.
Therefore, k plus 1's in A.
I have a question.
Why did you say then that k minus 1 is in it up there? What's the importance of that?
Because that's the proof.
So you can see the thinking from here to here.
Oh. And you know k minus
This
1
in N means it decremented is in N, is what it means to be in A.
decrement.
So, minus 1, sorry. When you decrement something, you remove 1. I don't know, that seemed like a normal thing to say, but I guess not.
I mean, I just didn't know what it meant. I don't know.
Oh. That really is a weird thing to say then. Is that, you don't hear
Yes.
decremented all the time, or
No,
incremented,
that was
decremented?
I've never heard that.
Oh my goodness. That must be computer science, then. That's all I can think. Okay. Okay, alright, continuing. So, I was just trying to show the parallels of what we're doing here. How do I show that k plus 1? If I want to show that k plus 1's in A, I need to show that k plus 1 minus 1 is in n, whenever k plus 1 is in n. That's why. I'm just writing explicitly what exactly it meant for k to be in A right here, and trying to help you see the parallels in the thinking. And I think you know how to continue the proof from there, right? Therefore k plus 1 is in A, therefore A is inductive, therefore A is equal to n, right? Now, if I were just doing this proof for some mathematician that's already out there and they just wanted me to prove this, I'd say something along the lines of base case, notice that 2 minus 1 is in n, which gives me that the statement is true for 2, something like that. I'm being very shorthanded here.
Why are we writing that?
Never mind. We won't.
No, I want to see that.
You do?
I'm just wondering why.
So then, k
It's just like a short little snippet.
in A would give me that k minus 1 is in n, and k in n. I'm going to make a mess doing it this way. I'd have to write a little bit more, but we just start here and go from there. We won't. I'm afraid I'll make a mess of it. And I don't want to take the time to
Okay,
put
now
in all the
question,
details I
now
need.
question.
Yeah, let's just do this.
Okay, go back up to n is greater than 1, then n minus 1 is a natural number.
Yeah. So we're proving this from 2 onwards.
Right, so how can we do that?
How can we do what?
From 2 onwards instead of, like, how can we just kick out 1?
Well, this statement is only true for 2 onwards.
If n is any number in n.
So here's what I prove here. Here's what A is. A is all the natural numbers that make the statement true, or it's 1.
Okay, but 1 doesn't make it true, so how
Right.
can A be?
That's why I defined A to be all the numbers that make the statement true, or 1.
Oh, so it's either true or false.
So A is all the natural numbers such that when you minus 1 from them, it's still a natural number, or 1. So I'm saying if the natural number is 1, put it in A, or if the natural number makes a statement true, put it in A.
Okay, but how can n be 1?
1's a natural number. A is a set of all the natural numbers such that that number is equal to 1.
Okay, go up though, like up here. Yeah. N can never be 1.
Right.
So how can we put that in A?
If n, okay, the n here and the n here are not the same n. N down here is just a dummy variable. So
Wait,
maybe
what?
that's where your confusion comes from. So let's erase all the n's in here and make this x. Maybe that's where you get. So we are trying to prove that for every natural number greater than 1, when you subtract 1 from it, it's also a natural number. Right?
Besides 1.
Besides 1. So we're trying to prove that this statement's true from 2 onwards.
Because it says greater than 1.
Yeah.
Therefore, we already know that it's greater than 1.
Well, down here when I define A, I say let A be all the natural numbers that are either 1 or that make the statement true. So A is going to be 1 or everything else that makes the statement true. If it turns out that A is all the natural numbers, then all the numbers that made the statement true were 2, 3, 4, 5, 6, 7, 8, 9. Everything except 1. So proving that A is a natural numbers.
How can A be all the natural numbers except for 1?
No, it's all the natural numbers.
Oh, wait.
It's either 1. So imagine I'm telling you, let's create a set. I say, I want you to do 2 things and put 2 things in the set. First, I want you to put 1 in the set. Now, I want you to put all the natural numbers in the set such that when you subtract 1, it's still a natural number.
Okay.
Then what are you going to put in here? 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, all the other natural numbers. Right? When it's all said and done, you would have put all the natural numbers in here. So proving that the statement's true for 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 is the same thing as proving that this is the natural numbers.
Okay.
You see it now?
Yeah.
Okay.
Sorry.
No, when I first came across this, it took me a second to figure out how to do it because handling that just felt so weird.
Yeah.
It feels like you're doing it wrong, like, we're gonna force this to be in here even though we actually can't.
Right, so you're putting things inside your set that don't satisfy the statement, just so you can show that your set is all natural numbers.
Yeah.
Instead of showing your set
Yeah.
explicitly is just those numbers that satisfy the equation, you make it all natural numbers, and you notice that but one we just put in there.
Works great.
Okay. So maybe we should specify more when we're done with this. Therefore, k plus 1 is in A, 7. Therefore, A is equal to N. Therefore, our statement, whatever, I don't want to write that out, is true for all natural numbers minus 1. Because we explicitly put the 1 in there. So when we take the 1 out of that set now, then we're just left with the numbers that made the statement true.
Why did you say S?
S is just the statement.
Oh, okay.
Therefore, S, the statement,
Right, okay.
is true for, I just don't want to write out the statement. We good?
On that one, yes.
That one's also on the test.
Okay, that seems something that we could probably do.
All right, what else?
Well, 8 and 9 are follow from 7.
Yeah, so now 8, so the same way that we had to use a natural number plus 1 is a natural number when we were proving that the sum of two naturals is a natural. Now you're going to use the fact that a natural minus 1 is a natural for proving 8. Was I looking at 8 right? Yeah. So 8 is proving that if you have two natural numbers such that one's greater than the other, then their difference is still natural. You prove it's true when you're taking away 1, you assume it's true when you're taking away k, and show that's true when you're taking away k plus 1, or when you're taking away k and then taking away
So
1.
you have to do the same thing here, because
So
you
it's
can't go
the
1
same
minus
thing
1 and
then.
have it.
You use this proof twice in there. You use it for your base case, and then you use it again when you do your k plus 1.
We did the K plus 1 though, right?
Yeah, for this. I'm saying for 8.
Right. So it's the same thing.
It's very similar
So, but
to the first proof we did.
in 8,
It uses this one.
you're going to have the same thing where it's either x is 1 or it's a natural number.
Yeah, you're going to start out with let n be a natural number, and let n, or sorry, this one you're going to do different. Let n be a natural number, and then make A the set of all natural numbers m such that m is less than n, and it satisfies the equation.
Right.
And then you induct on n.
But don't you have to put 1 in there, just like here? 'Cause you-
Yeah, so we're going to have to subtract 1, and then subtract 2, and then subtract 3, and subtract all the way to
What I'm saying is,
n minus,
you can't, 1 minus 1 is not in that sense, so you have to say that or
alright.
1.
It's faster to prove it than have all the conversation about how to prove it. And I think you'll see right out the door how we use this. So now I know that if n is greater than, I know that n minus 1 is a natural number if n is greater than 1, right?
Mm-hmm.
So we're proving that,
So now assume that
prove,
N
if
is 1.
n is a natural such that n, well, we need n and m are naturals, huh? If n, m are naturals such that n is greater than m, comma, then n minus m is a natural. That's what we're trying to prove, right?
Yes.
So I'm going to induct on what we're subtracting. I'm going to induct on m. So I'm going to say let n be a natural number, and then I'm going to do my induction on m. So let n be a natural number, to let A be the set of all natural numbers, all m in n, such that m is less than n and n minus m is in n.
Right.
Three. Observe that if n is greater than 1, then n minus 1 is in n from our previous proof.
Right.
4, therefore 1's in A.
Alright, that makes more sense.
1 is in A. Let n be a natural number and observe that, well, here's the one special case I'm trying to keep in my head. I'm trying to keep in my head, what if n is equal to 1?
Right.
So I put some note at the start, something along the lines of, observe that if n is equal to 1, then the set of natural numbers we can subtract away from it is the empty set.
Because the empty set is a subset of the natural
The empty set is a subset of everything, so it's a subset of natural numbers. So the empty set would be all the natural numbers that satisfy the statement. So I break this up into two cases, one where n is equal to 1, and then the answer is just the empty set. And then I say, okay, now assume that n is greater than 1, and then continue from here.
So we need to assume that n is greater than 1.
From here on out. So you know how you would handle, if n's equal to 1, blah, 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 blah. So let n and n such that n's greater than 1 now. And continue from there. You understand why we need that quick specification? So let n be a natural number such that n is greater than 1. Assume that n is blah, 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 all these things. Observe that since, not if, since n is greater than 1, then n minus 1 is in n. Therefore, 1's in A.
We say that n minus m equals the empty set. Is that how you say that? I'm sorry, back up at the top. If you say, if n is 1, then n minus m is the empty set.
Then,
N is the empty set. No.
well, just however you want to put it. So first now, okay, here's what we put at the top. If n is 1, comma, there are no m in n such that n is greater than m. Okay, now continue.
Okay.
So let n be a natural number such that n is greater than 1. And then continue. Just make sure you give the reader some note, hey, we're justified in making sure n is greater than 1. Okay, so let n be greater than 1, then this. We're good so far, right?
Yes.
Now assume k is an A. What do we know if we know k is an A?
K plus 1 is.
Well, that's what we need to show. But if k is an A, then that means k is a natural number, and k and
Assume that. That implies
then we
K
know
plus
that
1.
k is less than n and k minus 1, not minus 1, k minus n minus k, I keep doing this backwards, and n minus k is in n. Right?
Yeah.
Wait. Oh, yeah.
Now we have two cases. Either k plus 1 is equal to n, or k plus 1 is still less than n. Right? If k plus 1 is equal to n, then what?
Why can't it be greater? Oh, because K is not.
Because when you add 1, then
Right, okay.
you whether we've either gotten n or passed n. So, if k plus 1 is less than n, let's handle that case first, since this is the case that we care about. if k plus 1 is less than n, then since n minus k is in n, then n minus k minus 1 is in n.
How do you know that?
Previous proof. If a natural number is in n, then that natural number minus 1 is in n. Oh, sorry. If k plus 1 is greater than n, what does that mean? I need to specify this. Then that means that n minus k plus 1 is greater than 1. Greater than or equal to 1. Right? How did we have it set up before? We said if a natural number is greater than 1, oh, sorry. N minus k is in n. If k plus 1 is less than n, then this means n minus k is greater than 1. There we go.
There we go.
Okay, sorry. So here's the flow. I made a mess. If k plus 1 is less than n, then you know that n minus k is greater than 1, right? From our previous proof, since n minus k is greater than 1 and n minus k is in n, then when you subtract a 1 from it, then it's also an n. That's what the previous proof was.
Yeah.
Every natural number greater than 1, so it's greater than 1 and it's a natural number, then when you subtract 1, it's still an n. And then if k plus 1 is equal to n, then we're not interested in it, right? I don't know how we want to say that. How do I write it in here? We just need to handle the cases where it satisfies a condition. So, we're good with that. Because if it doesn't satisfy the antecedent, then the conclusion is automatically true. Therefore, how do I end that? I guess we could have constructed the A different, right? So that it had all the natural numbers. Let's see, how do we do that? Let A be the set where m is less than n and this is true, or m is greater than or equal to n. So we get all our numbers greater than or equal to n in there for sure, and then we show that the rest is inductive. But that's the gist of the proof.
So what needs changed? I'm missing.
So I'm fine with this thinking right here.
Right.
I'm just saying if you want to show instead that A was inductive, then we would specify let A be the set of all m that satisfy this, or all the n's greater than or equal to n. Right?
What's the point of doing that?
Then I can show that A is all the natural numbers. Instead of saying, therefore, if it's a natural number that satisfies this condition, therefore, if it's a natural number that satisfies this condition, then it satisfies this. I'm fine with you thinking about it just that way. Show that if it's a natural number that satisfies this, then it satisfies this. But if you wanted to prove it was true, if you wanted to show that A was all natural numbers,
Which is what you need to do to prove it, right?
no, because it's not true for all natural numbers. It's true for all the natural numbers that satisfy this condition.
But
But you remember before, since we just had a 1 to deal with, we just threw the 1 in there.
yeah.
Here we didn't even show that it was all those numbers. Here we just showed, basically decrementing, we showed, look, it works when you subtract 1, and it works when you subtract any number, all the numbers that you can subtract up to a certain number, it's true for. And if we wanted to get all the rest of the numbers after that, then we would have needed to change A to include all those numbers. So we would have said, it's all the numbers that satisfy this, that you can take away, or it's equal to it, or it's greater than it, and therefore it's everything.
What are the numbers that don't satisfy that?
N, for example. N is a natural number that doesn't satisfy this. N minus n is not it doesn't satisfy the condition.
But n isn't less than n.
Right, that's what I'm saying. N is a number that wouldn't be an A. So we have A here, and I'm saying if we want to make A equal to N, we need A to equal, or we'd have to take A, we'd have to union N in there. Well, let's just say it this way. We'd have to union all the X such that X is greater than or equal to N. So if we take A, union this, now we have all the natural numbers. A is just all the natural numbers less than N. Union it with this, now you have all the natural numbers.
So,
If doing it with all the natural numbers is just adding confusion, don't do it
what I'm
that
saying
way.
is to prove it inductively, don't you need all the natural numbers?
To prove it inductively, don't you need all the natural numbers?
You have to prove that A is equal to n.
Yeah. So if you want to do that, then make a new B, let B equal A union this thing, and if A is the numbers that we expect it to be, then this is now N. You could do that.
And that's proving it.
And that would prove it, sure.
And then on your last line, thing.
What I'm saying is if you completely understand just showing it for A, we don't need to bother with all this extra work making it equal to N.
Right, but I mean, you're supposed to, aren't you? Technically.
Well, technically, depends on how technical you want to be. Because you know there's a lot of technically you could add. If we prove this thing technically, it blows up.
Right.
So the question is do you need to add it for clarity for people to understand that the proof works?
Probably not.
And if the answer to that question is yes, add it. If the answer to that question is no and it's just making a mess of it, don't add it.
Okay.
So, I mean, it's somewhat a judgment call, but I think you understand the proof, right?
Yeah.
Well, how does your line 6 prove that k plus 1 is an A?
Okay. Let me rewrite this. Sorry.
Oh, okay, I see.
Good? Okay, so we good now?
There's still 9.
9?
Well, 9 comes from 8. That's why when we got stuck on 7, and that was it.
Prove that the sum of any two integers is an integer. Did we not do that in class?
No, we said this is a homework project you do on your homework.
Oh.
Some difference in product.
Yeah,
I
but
feel like we did, oh.
So we have to prove the sum difference and product.
so we'll just do the sum. Don't bother with the rest if you don't have them, because it's just to help you understand how you would do these types of proofs. And I think if you can do one, you can do all. So we'll just do the sum real quick. And the only trick with this problem is remembering, hey, do you remember what the definition of an integer is? Is basically what we're referencing back to, right?
I looked it up. I can remember.
Good, glad you looked it up. So proof that for all m, n in Z, then, let's see which one we're doing. We're going to do plus. M plus n is in, not n, is in Z. Okay. So, let's see. So we need to handle the cases where the positive and negative combinations and then 0, right? So 1, let m n in Z. 2, observe that if m equals 0, then m plus n is equal to n is in Z. And if n is equal to 0, then m plus n is equal to m is in Z. So if either one's 0, then obviously their sum is still an integer, since we were adding integers, right? Then, for m n not equal to 0, we have 4 cases. Case 1, m is in n, and n is in n. 2, negative m is in n, and n is in n. Oops. 3, we have m is in n, and n is negative n is in n. And 4, we have negative n is in n, and negative n is in n.
Why do I feel like we haven't done this before?
We've basically handled all these cases. I want to try this in. It's trying to hurt. But do we understand why these are the 4 cases that we need to prove now? These were all the possible combinations. Either one of them was 0, or they're both positive, or one of them is negative, or they're both negative. And these 2 cases you see are really the same case,
Yeah, they are.
probably, right? Okay, so 4. Observe case 1 is done.
Why is it done?
We already proved that the sum of 2 naturals is a natural.
Right.
Okay, case 5, we'll assume, let's see, we did n is a natural, and then it's negative is a natural. Negative m is in n. Okay, let's see how I want to say this. Oh, and then I had to break it up into cases like that. So we got to do cases within cases here.
Oh boy.
So if n is greater than negative n, comma, then n plus negative m is equal to n minus m is in n based off of our proof that we did before. If this is bigger than this, if n is bigger than m, then that is a natural number.
Why not just say that? And wait a minute.
Oops.
Are you?
Sorry. You're looking for n plus m. Then n minus
There we go.
negative m, sorry,
That makes more sense.
is equal to n plus m is in n. Thank you. We're proving that if negative m is positive, right? Remember, negative m is a positive number. It's natural. So a natural is bigger than a natural. Then a natural minus a natural is still an n, and we can rewrite that natural minus a natural as n plus n. N plus n. So that's natural. Right? Now, if n is equal to m, then it's obviously going to be 0, right? And n minus negative m, which is the same thing as n plus m, is going to be equal to 0.
So they're the same case.
which once again is a natural number. And then finally we have the case if n is less than negative m. If n is less than negative m, what does that mean? It means that if n is less than negative m, we have negative, let's see, let me see my writing and then come back to it. Then negative n plus m is equal to negative m minus n is in n, which gives n plus m is in z. So let's see if we can understand that real quick. So n is less than negative m. Did I write that right? N is less than negative m, yep. Then negative n plus m. How did I get there? If n is less than negative m, then
Well, n is negative.
Because n is negative.
n isn't negative. N's a natural number and negative m is a natural number. So let's just write some scratch work to see what I was thinking. So this means that n minus negative m is greater than 0, or in other words, this is a natural. So I know that this is a natural. So then
Isn't it switched around? Isn't it negative n minus?
oh yeah, I'm looking at the sign backwards, thank you. I know that negative m minus n is a natural, which can be rewritten, there we go, as negative m plus n is a natural.
Okay.
And since the negative is a natural, then the number itself is an integer. Because remember, what's an integer? It's a set of all the naturals or their negatives. Or 0. So if a number is a natural, or the negative of a number is a natural, or it's 0, then it's an integer.
Right.
Right? So that proves case 2 and 3. They're really the same case, right? And then let's handle the last case. So 6, assume, let's see, assume negative m is in n and negative n is in m, or is in n. So what does that give us? So we know that their sum's in n. Then negative m plus negative n, which is the same thing as, maybe we'll put parentheses, which is the same thing as negative n plus m is in n, which gives us that n plus m is in z. And we're done.
Is this going to be on the test?
I honestly don't know what's on the test.
Because that's kind of a long proof to
Tricky
just
one.
remember if you forget a step.
Yeah, this one's on inductive one. You're just using all the inductive proofs that you've already used. Right? Okay. So that takes care of homework, right?
Yes.
Actually.
I'll do it.
Yeah, I told you that this class, the homework is on a new level. It's not like the discrete math homework, which is why you're more than welcome to use any resource you can find to do the
Yeah,
math.
it really is quite difficult.
Yeah. So it's fully expected that you would come across homework problems and be like, I have no clue where even to start, and to start Googling around to figure out how to start. And that's perfectly acceptable. Can you see the camera?
Yeah.
Tell me when I'm good.
You're good. Right
Good? Okay. All right. So the next section. Section 1.2. There's two big ideas that we're trying to cover in section 1.2 and try and give them to you in a nutshell. So imagine the real number line for a second. 0, 1, 2, 3, -1, -2, -3. The question is it possible, so we're going to be looking at intervals of numbers, and what we're interested in is how often do we get an integer in an interval, and how often do we get a rational in an interval? So when I'm looking at an interval of numbers, here's an example of an interval of numbers, here to here. How many integers do I have in that interval? 1, 2, 3, 4, 5 integers are in that interval. Okay, so one of the questions we might naturally ask is, can I get an interval so small that I don't have any integers in there?
Yeah.
Yeah, if I take this teeny interval, there's no integers in there, right? So then we say, okay, how big of an interval do I have to be guaranteed I catch an integer?
1.
And then a similar question is, what about rationals? So we know that some of our numbers are rationals and some of them are irrational. So if I were to sit there and plot all the rational numbers, plot it on here, if I were to plot all the rational numbers that there are, is it possible for me to get an interval so small that it only contains irrationals and there's no rationals in there? If I keep zooming in, can I eventually get to the point where I just have my interval is just irrationals?
Yeah.
Yeah, obvious. What?
Yeah.
Yeah?
Yeah.
No!
Right.
And we'll prove it. So that's what we're going to prove. We're going to prove
if your interval is only one number, isn't that
open interval.
Oh.
Open interval. So we're looking for an A, B open interval. Is it possible for me to put A and B so close together that it only contains irrationals? And the answer there is no. So we're going to prove what interval you have to be guaranteed that you get an integer, and then we're going to prove that no matter how small of an interval you always have a rational. Those are our two big proofs. So the two big proofs are this one. For every real number, there exists one and only one integer in the interval closed on this side from c to c plus 1. So in other words, I'm guaranteed that pi to pi plus 1 contains one and only one integer.
Okay.
For any real number I pick, plug it in here and here, I'm guaranteed that interval contains one and only one integer. And then the other big idea is to prove that no matter how small we make that, we're always going to have a rational. The way that we say that is the rationals are dense in R, where R is our set of real numbers.
What does it mean to be dense?
It means that no matter how small of an interval you take, you're guaranteed to get one. So we'll prove that the rationals are dense and that the irrationals are dense. So that's the big idea with 1.2. So let's prove the big idea. And these are the theorems that we're going to prove along the way. So the first thing that we need to prove is called the Archimedean property. We need to prove that for any real number you pick, I can always find a natural number bigger. Make sense? And let's remember where our proofs ended last time. Last time, one of the big ideas we were talking about was, what does it mean for a set to be bounded from above? It means I can find a real number greater than or equal to every element in the set, right? And we had the idea of a supremum. This was an axiom. Every set bounded from above has a least upper bound, a supremum.
That was an axiom?
Yes, that's the completeness axiom.
Oh, yeah.
Our last axiom. So I'm guaranteed, if I have a set bounded from above, that it has a smallest upper bound. And we're going to be using that. So let's do this real quick. So prove that for all C in R, when we do a plus up there, we mean the positive R's. So for every positive real number, there exists a natural number such that the natural number is greater than the real. So for any real number you pick, I can always find a natural number bigger, is another way to say that, right? So let's prove it. Assume by way of contradiction, that's not true. Assume by way of contradiction that there exists C in R such that C is greater than N for all N in N. Right? If it's not true, then it means I can find a natural number, or that I can find a real number bigger than every natural number. Right? That's going to be the opposite of that statement. So, proof by way of contradiction. Assume that we can find some real number bigger than every natural number, and we're going to show at least a contradiction. 2. Then C is an upper bound for the natural numbers. Right? That's what it means. If it's greater than every natural number, it's an upper bound. And we're guaranteed that if a set has an upper bound, it has a least upper bound. Let B equal the supremum of N. So whatever the least upper bound is, we're going to call it B. So since C is an upper bound, there's a least upper bound, call it B. For since B is the supremum, then B minus 1/2 is not an upper bound.
B minus anything.
Yeah, B minus anything is not an upper bound. B is the smallest upper bound, therefore B minus 1/2 is not an upper bound. If it's not an upper bound, what does that mean? It means there's an element in the set greater than it. Right? So 5, so then there's a natural number bigger than B minus 1/2. Then there exists M in N such that M is greater than B minus 1/2. But if M is greater than B minus 1/2, M plus 1 is greater than
B plus 1/2.
B plus 1/2, sure, which is greater than B. However, n plus 1 is a natural number. There's our contradiction. We found a natural number greater than the supremum of the natural numbers. Doesn't work. Therefore, no such C exists. Make sense? And we're done. Any questions about that one? This Archimedean principle is something that we reference over and over and over again. You're going to use this, once we start proving limits, we're going to use this principle non-stop. So let's make sure we understand it. For any real number you pick, doesn't matter how big of a real number you pick, I can always find a natural number bigger. That's what we just proved.
So you're saying the supremum basically is...
Basically,
it's pretty small then.
Basically, we proved that the natural numbers aren't bounded from above. They go on forever, so to speak. Right? Our big problem was we assumed that there was a natural number bigger than all the natural numbers. If there is a number bigger than all the natural numbers, then there's a smallest number bigger than all the natural numbers. But then we found a natural number bigger than the smallest number bigger than all the natural numbers, which is a contradiction.
The well-ordering principle in discrete math basically the completeness axiom?
It gives us what we need.
For discrete math?
Yeah, it gives us what we need to do a proof like this. It's very similar. What was the well-ordering principle? Is that every subset has a least element. Because we were always talking about discrete sets. So in discrete math, if a set's bounded, its max element was always the supremum. We never dealt with sets that were bound that didn't contain their max element. So we didn't need the completeness axiom, but it's a similar idea. Okay, so we get a lemma from this right out the door. Or a corollary, sorry, not a lemma. The corollary that we get from this is that for all epsilon in R plus, there exists n in n such that 1 over n is less than epsilon. So let's make intuitive sense of this proof real quick, or of what we're trying to prove. So typically we use epsilon to represent a really, really small number.
Why? What do you mean really, really small?
I mean a really, really small number. The same way that when we use n, we're typically referencing a natural number. When we use epsilon, we typically mean think of something really small. Like 0.0001. Pick any real small number you want. I can always find a natural number so that 1 over that natural number is smaller than the really small number you thought of.
Oh, yeah, that makes sense.
Does it make intuitive sense? Okay, so now let's prove it, and we're just going to use this.
I think, is that supposed to be a less than sign?
Yes. Thank you. All right. 1. Let epsilon be a positive real number. Doesn't matter what it is. We can always find one smaller than it. 2. By Archimedean property, there exists n in n such that n is greater than 1 over epsilon. This implies 1 over n is less than epsilon. Just doing the algebra. Divide both sides by n, multiply both sides by epsilon, and you get that. I also flip the sign. Maybe write it this way. Then epsilon is greater than 1 over n, or 1 over n is less than epsilon. So, epsilon is just a positive number, right? Now we know that 1 over epsilon is also a positive number. That's one of our old proofs. If a number is positive, then its multiplicative inverse is also positive.
Okay.
Right? So 1 over epsilon is positive. By the Archimedean property, for any positive number, namely 1 over epsilon, I can find a natural number bigger than it. If n is bigger than 1 over epsilon, then epsilon is bigger than 1 over n. Multiplying both sides by epsilon, divide both sides by n, is one way to say it. What's weird?
That doesn't look like what you did. If you multiply both sides by epsilon, you get epsilon times n.
Is greater than 1.
Is
Now divide both sides by n.
Oh, okay.
You see it now?
Yeah.
Any questions about this proof?
Do we also prove that for any number you choose, we can find a smaller natural number?
No, because that's not true. I can't find a natural number less than 0.5.
Duh. I guess it'd be integer.
Okay, so we proved theorem 1.5 and we proved the corollary that comes right after. Those two things you're going to use for all our proofs with limits. That's what you're going to reference over and over again. Alright, let's prove the next one. Let's just say it. Prove that for every natural number n, comma, the interval n to n plus 1, n to n plus 1 does not contain an integer.
It can, but it
No.
doesn't necessarily always.
No interval from an integer to an integer plus 1 contains an integer inside of it.
Because integer can be like. Wait, what? No, that's
Give
not
me
what
any
it says.
integer you want.
What's an integer?
a natural number, a negative of a natural number, or 0. So
Negative
-4
5.
to -4 plus 1, which is -3. This interval does not contain a natural number, or does not contain an integer.
How?
So this interval, remember that this is the same thing as a set of all x in Z.
Hang on, wait. Why
Or,
can't
sorry,
you do
is this-
-4 to 3?
It has to be from n to m plus 1.
Oh.
You see it now? Okay. So we're proving that no interval like that contains an integer. 1. Let n be any integer, doesn't matter. Right? 2. We're going to handle the case of 0 to 1 first.
Oh, we're proving it by induction.
No. Well, we don't need to handle it for this case. We just need to say that 0 to 1 doesn't contain an integer in general. So observe that 0 to 1 is logically equivalent to the set of all x such that 0 is less than x is less than 1. Since the smallest are all positive. So these are all positive, right? Because they're all greater than 0.
Dude, what? Can you define positive?
Greater than 0.
But our textbook doesn't say that.
We went over that when it came up. So x greater than 0 is logically equivalent to x minus 0 positive, which is the same thing as x positive. So I told you I'm going to go back and forth between saying x is positive and x is greater than 0, logically equivalent.
When we talked about the set of positive numbers, all we were told was either x is positive or negative x is positive. Or
When we defined this symbol, we said, what does it mean for x to be greater than y? It means x minus y is positive, whatever positive is. And if x minus y is positive, or sorry, now if y is 0, then x minus 0 is the same thing as x. So saying x minus 0 is positive is the same thing as saying x is positive. Therefore, x is greater than 0 is identical to saying x is positive. Our definition for x is greater than y was x minus y is positive. That was our definition.
okay.
So when you plug in 0 for y, then there.
So any number.
So from here on out, you can say, instead of saying a number is positive, you can just say it's greater than 0.
Awesome.
So I wanted to do that little proof first thing when we did last time because I said it's so convenient to go back and
So I
forth.
forgot we did that because that
Yeah.
was the
It's easy to forget. We covered a lot of proofs. Okay, so anything from 0 to 1, whatever it is, it has to be positive, right? Since the smallest natural is 1, then the smallest positive integer is 1. Because all the positive integers are naturals, right? Because the integers
We proved that.
are the naturals. Well, you could prove this by induction really quick if you want. Prove that every natural number is greater than or equal to 1. Okay, prove it for 1. And then if it's true for k, it's true for k plus 1. Done. Right? So you can do that if you want, but we're good. So you understand what we have here so far? Okay. Then, I don't know how to say there does not exist. There does not exist a k in Z such that k is also in 0 to 1. This is basically what we're getting at. 0 to 1 does not contain an integer. Because these are all positive numbers. These are all positive numbers. And the smallest positive integer is not in there. In other words, there's no integer between 0 and 1. That's what we have. Good? So then, we go back to n. Or let's say this. Assume, by way of contradiction, that this is kind of 2 person 1. Prove that this doesn't contain 1. Now we're going to come up and prove this in general. Assume by way of contradiction that there exists k in z such that k is in n to n plus 1. So assume that n plus 1 contains an integer, and we're going to show that that leads to contradiction, which the contradiction is going to be, we're going to show that that would imply that there's an integer between 0 and 1. So what does it mean for k to be in n to n plus 1? Then n is less than k is less than k plus 1, or n plus 1, right?
Right.
That's what it means for k to be in this interval. It's greater than n and it's less than n plus 1.
Right.
So if we know that k is between n and n plus 1, we know that 0 is less than k minus n is less than 1. Which implies k minus n is in 0, 1.
You just
Contradiction.
You're using the definition of.
We're using the fact that an integer minus an integer is an integer. So your homework problem was to show that the difference of 2 integers is still an integer, right? So k is between n and n plus 1. Here's our inequality. We're going to subtract n from, I was going to say both sides, but from all 3 sides, if we can say that. So n minus n is 0, k minus n is k minus n plus 1 minus n is 1.
Okay.
So if k is between n and n plus 1, then k minus n, which is still an integer minus an integer is an integer, would be between 0 and 1. And we know that there are no integers between 0 and 1.
And that's because. Wait a minute. How do you know n is an integer? We never said that n is an integer.
Right at the top.
Ah,
Let n be an integer.
yes. Right. Right there. Okay.
Questions?
I think it would help a little if you explain what you're doing while you do it. Because the second you explain it, then it clips.
Well, it's hard to write and explain, so I kind of need to get up there then explain what it says.
Okay.
Anything else? Good to go? Next one. Prove that the set of integers, if a set of integers is bounded from above, then it contains a max element.
So when do we start, when do we understand and kind of clarify that all the natural numbers is a continuous number line with decimals? And we start representing these with decimals.
When do we get to decimal numbers?
Yeah.
I'm not sure. Probably the next section.
And like clarify that there's order that, just like get an actual order to the number line.
Well, we already have an order to the numbers.
It's just kind of.
So,
sketchy.
ignoring the completeness axiom, we now have perfect orders for all the rationals, and we can now construct any rational number you want, and we can talk about any rational you want, and we can have it completely defined in terms of our axioms, just using ones and zeros.
Because of the positivity axioms, right?
Because of the positivity axioms, we can put them in order, and because of what we've proven, we can create any number you want. So, for example, you say, okay, prove that 5/3 exists. You might say something like that.
Prove that it exists.
Yeah. Prove that we have 5/3 in our system of math that we've been developing. Right? Our definition for 5 would be something like 1 plus 1 plus 1 plus 1 plus 1. That's our 5. And we have this times 1 plus 1 plus 1 to the negative 1. We know what that is. We define that symbol. We know what 1 is. That was given to us in our axioms. We know what plus is. We know what times is. We know what plus is. We know what 1 is. We have this number. And I could talk about this number plus a number and prove that it equals whatever it equals. And I could talk about the ordering of the numbers if we want. But So, yeah, right now we can talk about all the rational numbers. We can talk about operations on them, have it all perfectly well defined. And then we can also for the reals, but we haven't gotten to the decimal expansion of them yet. Because a real number is going to be basically any number you can make with an infinite decimal expansion. We're going to prove that I think we're going to prove that every real number can be captured that way. We'll get to it. All right. Moving on, which one were we doing? A set of integers bounded from above contains a max element. So how do I say it here? Non-empty set of integers bounded from above has a max element. You know what I mean by max, right?
Yeah.
There's a biggest thing in there. Now you might think, isn't this true for every set of numbers? And the answer is no. For example, consider the interval 0 to 1. What's the biggest thing in there?
0.9 repeating.
1's not in there. This is a set of all the x between 0 and 1. What's the biggest thing in there? The answer is there isn't a biggest thing in there.
That's pretty.
dumb.
That's weird.
We can prove that there's no biggest thing in there if you want, but let's assume that c is the biggest thing in there,
Okay.
right? Well, notice that c plus 1 divided by 2 is going to be, c is going to be less than this. C is less than the average of c and 1 because c is less than 1.
Okay.
Right? And this is in there.
How do you know what's in there?
This is less than 1 plus 1 over 2. Alright, let's write this. C plus c over 2. That's the same thing as c. So c is equal to c plus c over 2, right?
Okay.
Since 1's greater than c, remember c is in this interval, so it's less than 1. Since 1's greater than c, then c plus 1 over 2 is in there. But since c is less than 1, 1 plus 1 over 2 is bigger than it. So this is a number less than 1. This is equal to 1. This is a number between 0 and 1 bigger than c.
Oh, we said c was the max.
We said c is the biggest. Let's assume that c is the biggest thing in there. Well, then no, this is bigger.
Right.
So there is no max element in there. Okay. So it's not trivial that every set has a max element. It's not obvious just because it's bounded that it has a max element. That happens to be true with the integers. It's not true in general.
Okay.
And it's not even true for the rationals. Because what we just constructed was a rational, so that works for the rationals.
Right.
Okay. No, that's wrong one, that's wrong one, where are we? Okay. 1. Let A be a set of integers bounded from above. And note that A is not equal to the empty set, where A is not the empty set. Should have said that better, but let's keep going. Now, since it's bounded from above, it has a supremum, completeness axiom. So now let's call little a the supremum of A. What we're going to prove is that its supremum is actually inside of it. That's what we're going to prove. That's how you show it's that the max element's in there. So for example, let's look at the interval 0 to 3 close bracket. Notice now 3's in there. And 3's also the supremum.
Right.
So if the supremum is inside the set, then it's the max element. Does that make sense?
Wait a minute, what? How can the supremum be inside the set?
For it to be an upper bound, so C is an upper bound if it's greater than or equal to everything in the set. 3 is greater than or equal to everything in the set. Right?
Okay, wait, what?
Okay, so what is this shorthand for? This is the set of all x such that 0 is less than x is less than or equal to 3.
Okay, that's so strange to me.
This interval notation?
Yes.
Okay, but here's what it is. So does that make sense? That's a 3, not a curly brace. So this is shorthand for the set of all x, where x is greater than 0 and less than or equal to 3. So 3 is in here. It's not in here. We have two ways of doing it, right? This means don't include the 0 or the 3. This means don't include the 0 but do include the 3. So in this case, 3 is an upper bound of this set. Everything in this set is less than or equal to 3.
Okay. How do you know the difference? Like, so 0, 3, right? So then the set that is interpreting or whatever is just 1, 2.
No. This is a set of all real numbers between 0 and 3. 0.5 is in here.
Whatever, I'm just saying between those two. So you write out a set, but how do you, like, determine the difference? Like, that looks like a normal set to me.
The difference between this and this?
No. No, that's not what I'm saying. Okay, look at 0, 3. How can you tell that that is implying a different set?
Okay, so this is not the same thing as 0, 3.
Okay.
And it's also not an ordered pair like we did in
Right.
discrete math.
That's what I'm saying. Like, how can
This is shorthand for this. Get rid of this. We're saying we're going to use these round brackets in two ways. You're used to seeing us use it to represent an ordered pair. In this context, we're not talking about that way. We say that another way we're going to use this kind of symbol is to talk about a set like this. It's shorthand for talking about a set like this.
Right. So
It's a set of all the real numbers x.
Okay.
Should have specified x and
I
r.
get that, but is that the only way that we're going to use it, or are we going to switch back to it being an ordered pair?
Sometimes we'll use it as an ordered pair. Sometimes we'll use it that way, and then obviously we also use parentheses just when we're doing math. X times a plus b. So we use those parentheses a lot of different ways. So you just have to infer from context what we mean by it. Right? So in this case, 0 to 3, this is all the numbers between 0 and 3, including 3. Since we have the square bracket on this side. Make sense?
Yeah.
So it makes sense that 3 is an upper bound of this set. Everything in this set is less than or equal to 3. Therefore, it's an upper bound.
Okay.
That's what it means to be an upper bound.
Right.
So, it's also the least upper bound. You cannot find a number smaller than 3 that's an upper bound of the set. Because any number smaller than 3 is going to be not bigger than 3, and 3 is in the set. So, if the supremum is in the set, then it is its max element. It's the biggest thing that can be in the set. Because it's an upper bound.
Right.
Make sense?
Yeah.
Okay. Okay, so let A be in the set, and then there exists M in A such that M is less than A minus 1. Sorry, other way around. A minus 1 is less than M. So, if A is a supremum, then something smaller than A is not an upper bound. A is a supremum. It's the smallest upper bound. So A minus 1 is not an upper bound, which means that there is some element bigger than A minus 1.
No, duh. A.
Well, not an integer element.
A is a supremum of big A. What's big A? Big A is Big A is just a set of integers bounded from above.
Yeah.
I said let little a be its supremum. It's the smallest upper bound.
Okay.
Then A minus 1 is not a supremum of that set.
Yeah.
Which means that there's something in the set bigger than A minus 1.
Yeah, I guess.
Yeah, it's not a guess, it's by definition of supremum. This is the smallest thing that's bigger than everything in the set. This is smaller than this, therefore this isn't bigger than everything in the set, therefore there's something in the set bigger than this.
weird, I guess, using a discrete set. All of the stuff we've done up to now have been continuous, with real numbers rather than integers.
And then I'm going to rewrite this one more way, which gives a is less than m plus 1. Whatever that element is, when you add 1 to it, you get something bigger than a.
Oh, okay. Yeah, that makes sense.
So I'm going to combine all this thinking into one little line. So m is less than or equal to a is less than m plus 1. M is less than or equal to a, how do we know that? A is a supremum. A is a supremum, therefore it's greater than or equal to everything in the set. And then, since a minus 1 wasn't the supremum, a is less than m plus 1. So this comes from the fact that a is a supremum. This comes from what we were doing on this line.
Right.
So you good with that inequality? Well, okay, we'll leave it like that so far. How can I say this? Well, I guess we'll just go about doing it this way. Then, let's see. Then A is a subset of the interval negative infinity to m plus 1. Basically, I'm going to say that there's nothing between m and m plus, there's no integer between m and m plus 1. Let me write it out and then I'll explain it. But since okay. Here's what we're saying. So, we know that A is between, the supremum A is between m and m plus 1, including m, right? What's A? It's, ultimately, we're going to show that A and m are the same element, right?
Why?
So remember I said if we can show that an element is a supremum, then it is a max element.
Yeah.
So we're trying to show that this m is a supremum. That's the idea. So we basically said, let's grab the m that's for sure within one of A. So grab the integer at the end of our set, basically. And then we're going to show we just grabbed the supremum, is one way that you could think about it. So remember, A is a, well, you're good with this inequality, right?
Yeah.
M's less than or equal to A is less than m plus 1. Now remember, A is a supremum of our set A. Little a is a supremum of big A. So I know that A, maybe write this to the side somewhere, write it over here. I know that A is a subset of negative infinity to A.
Right.
Since little a is a supremum, little a is greater than or equal to everything in A. So everything in A is going to be less than or equal to the supremum. Does that make sense?
Mm-hmm.
This is shorthand for all the numbers less than or equal to A. All the integers in A are going to be less than or equal to little a, since little a is a supremum. Right? So similar thinking on this line to this line. Since m plus 1 is bigger than our supremum, then A is also a subset of this. If it's a subset of this, and m plus 1 is bigger than A, then it's a subset of this. We just made the interval bigger. we couldn't have made it smaller. Does that make sense? Going from this to this, we made the interval bigger. But we know that m to m plus 1 doesn't contain any integers. So we can remove the m to m plus 1 part of this, which leaves us with this. Take this interval, get rid of the numbers between m and m plus 1. Should we write a number line for this real quick? Here's 0. We have our set of integers, a, whatever they are, but they're just those points, right? And then we grab our last element in there, basically, m, is right here. Now, a is a supremum. We don't know where it is. Here's a. Here's m. And then these ones over here are all the rest of our integers, whatever integers we have. Okay? So we said our set of integers, whatever they are, all these points back here, are definitely less than or equal to a. They're these points. And they're also going to be less than or equal to m plus 1. Right? But since m to m plus 1 doesn't contain any integers, then it's going to be a subset starting here going back. Because m to m plus 1, we're guaranteed there's no integer in there.
Because m is an integer.
Because a is a set of integers.
And m is in it.
Yeah, m's in it. But a is a subset of this thing, ignoring the fact that m's in there altogether. Since a is a subset of this thing, and since m's an integer, then and a is integers, then I'm guaranteed a is a subset of this thing. Because there couldn't have been any integers between m and m plus 1, and that's all we removed to go from here to here.
Huh.
Are you good with that?
Sure.
Another way of writing this is, for all x in a, x is less than or equal to m. That's another way to say this. Everything in a is less than or equal to m. Right?
Yes.
So m is an upper bound of a. What's our definition of little a? Little a is the least upper bound of the set big A. I just barely showed that m is an upper bound of the set big A. Therefore, little a is less than or equal to m. Therefore, m is an upper bound. 6. Therefore, the least upper bound, a. Therefore, a is less than or equal to m.
And so they're equal.
Therefore, a.
Up here we had m less than or equal to a. Therefore, a is equal to m, which gives us m is max element. It's really not that complicated. It's the first time you're being exposed to it.
Yeah.
So when you go home and watch the lecture, like I know you will, then you're going to find out, oh, that makes sense. You're going to have your that was easy button ready and you're just going to push it. All right. We are not going to get through the next section today. Not a chance, huh?
Your phone is at low battery.
How long have you been there? Is it really nice?
No, it's been about 10 minutes.
Why didn't you tell him?
It's 20%. There's no way it's going to die in 10 minutes.
Okay, but it stopped recording.
No, it didn't. I can see the numbers, so count it down.
Look where he is on the screen.
It's still going. All right. So it looks like we're not having a test next week.
Whee!
Shoot, dang it.
That's bad.
Yeah, it is bad because we're
I
getting
think
more
we're like
behind.
One behind.
Yeah, we are behind.
Oh well. Better that you understand what we cover than we cover everything.
Yes.
So don't feel bad about it.
We didn't spend so much time on homework.
And we got a late start and just a lot of stuff went wrong. Okay.
Spending on homework next time.
Yeah. Homework's just going to get harder.
Yeah, but now you have, thank you. Now you have your solutions that you know how to go find. So let's do the next one.
Kind of.
Hopefully.
But that doesn't mean I'll understand it.
You can sure try. All right, proof. Next, we're going to prove finding what we were working up towards. Every interval like this contains one and only one integer. So proof that for all C in R, for every real number you pick, there exists one and only one integer such that K is in C to C plus 1. And remember what this is shortened for. This is the set of all x in R such that C is less than x is less than or equal to C plus 1.
That's backwards. It's less than or equal to first, right?
Oh, yeah. It's going to be equivalent, but yeah, that's what we have. Good catch. Okay, so you understand what that's saying? Pick any real number you want. Give me one.
5.
Be more creative.
1/5.
1/5. That means 1/5 to 6/5, like that, is guaranteed to contain one and only one integer. In this case, it's
1.
1. Right. Okay. So let's do the proof. We're going to do the proof kind of in 2 steps. First, we're going to prove that there is an integer in there, and then we're going to prove that there's only one integer in there. That way, there's one and only one. Make sense?
Yep.
It's a common way we do.
So we're doing the exact same thing, only with the reals that we did with the integers.
We were always talking about the integers. The previous one was every bounded set of integers, every bounded non-empty set of integers has a max element.
1 up.
Oh, here we showed from n to n plus 1, if these are integers. Okay, I see what you're saying now. Yes. So this open interval was talking about integers. Now we're talking about if we have one side closed and one side open, and it's any real number, including integers, then it's guaranteed to contain an integer. Okay. Let's keep going. 1. Let C be any real number, doesn't matter. Comma. And let, what do we call the set? S equal the set of all x in R such that, oh, not in R, in Z, we're talking about integers. All x in Z such that, not such that, colon, we're doing set building notation. X is less than C plus 1. So get all the integers less than, we didn't write C, jeez. Let C in R. Grab some real number C, and we're creating some set of all the integers less than C plus 1. Okay? Basically, we're going to show that the max element in this set is in here. That's big picture what we're going to do.
Okay.
So here's a set of integers. First, we're going to show that it's bounded from above. Therefore, it has a max element. Therefore, the max element's in there. Therefore, that thing contains at least one integer. Assume it has 2 integers. Come up with a contradiction. Therefore, it has one and only one integer. That's big picture what we're doing. Make sense?
Okay, yeah.
Okay, so first we got to show that thing contains we got to show that S here contains an integer. 2. If C plus 1, or do I do C? It doesn't matter. If C plus 1 is greater than or equal to 0, then -1 is in S. All we're doing is showing that S isn't empty, no matter what C plus 1 is. Because we need to make sure this is a non-empty set of integers before we're guaranteed it has a max element. So first we need to do some busy work to show something already obvious to you, namely that S is not empty.
Can't you just say let S not be empty?
No. I need to show that for any real number you pick, that there's going to be an integer in here. And the only way that there's an integer in here is if I'm guaranteed that there's an integer less than C plus 1. So I need to guarantee to myself that there is always an integer less than C plus 1. That's one of the things I need to make sure is true if I want to say that there's an integer in here.
So you just choose a random example. That could have been 500 instead of 0.
Yeah, I'm just breaking it up into two cases. If c plus 1 is greater than 0, negative 1's in it. So was negative 10. So was negative 100. I'm just showing if c plus 1 is greater than or equal to 0, there's something in there. And then if c is less than 0, that's a c is less than 0, then there exists n in n using the Archimedean property such that n is greater than negative c, which gives me negative n is less than c, which gives me negative n is in our set S. Hopefully that's still on the camera.
It is.
Okay, you follow all that thinking there? If c is less than 0, remember, c plus 1, sorry. If c plus 1 is less than 0, then there exists natural numbers such that n is greater than negative c plus 1, which gives me, let's just go through this step and feel near to go. Alright, so c plus 1 is less than 0. By the Archimedean property, there exists a natural number bigger than negative c plus 1. Remember, if c plus 1 is less than 0, negative c plus 1 is greater than 0. So now it's a positive number. There's an n bigger than that, which is the same thing as I want it written this way. Negative c minus 1, whatever that thing is. Negative c minus 1, it's still a real number. I'm guaranteed that there's a natural number bigger than it, which is the same thing as saying that negative n is less than c plus 1. I just need to find an integer less than c plus 1. That's all I'm doing. Negative n's that integer. Oh, that's what I had here. Which means that negative n is in S. So either way, S is not empty is all we were trying to get at. Either way, S is not empty. That's all we were trying to do.
I'm like, what are we doing?
Right. That's how this proof feels at the start. It feels like we're doing a lot of busy work. All we're trying to show is that whether c plus 1 is positive, greater than or equal to 0 or less than 0, this set is still not empty. Okay, so now I'm guaranteed S is not empty. Therefore, it has a max element. Therefore, there exists m in S such that m is its max element. That was the beginning of our proof. Max element, call it K, just to stay consistent with my paper, in case I need to reference it. 6. Okay, so then we have
K just being a real number.
almost. So we got that K is less than c plus 1. Now I need to show that K is greater than or equal to C is the next part.
But it's an integer.
Since c plus 1 is the upper bound.
Okay.
Okay.
Can you explain line 5? There exists m in S such that K is its max element.
Oh, K. I need to replace them both with K. Sorry. So there exists a max element in S.
Oh, K.
There exists some K in S where K is its max element.
Oh, okay.
Sorry. Good catch. I shouldn't have switched my variables maybe. Okay, now I need to prove that K is greater than or equal to C. So I know that K is less than C plus 1, because it's in S. Now I need to show that K is greater than or equal to C. Remember, I'm ultimately showing K's in this ink. So I know K is less than C plus 1. Now I need to show it's greater than or equal to C, therefore K's in this ink, and we're done. Or then we've shown the existence part, then we need to show that there's one and only one.
S is equal to that interval.
Yeah, S is this interval.
You don't have...
It's not this interval, it's this interval.
Oh, okay.
So look, S is equal to, if we do interval, negative infinity
Right.
to C plus 1.
Right.
Now I found the max k, not s, is equal to that. Sorry, s is a subset of that. Because it's just the integers.
Right.
Right? So s is all the integers in here. I got its max element k. So I know that k is less than c plus 1. If I can show it's also greater than or equal to c, then k will have been in this interval. And I'm trying to show that this interval contains an integer k, and it contains only one integer k. So I'm going to show it contains an integer k, and it doesn't contain 2. And we're done. So, I've got that k is less than c plus 1. K, the max element in s, is definitely less than c plus 1. Now I need to show it's greater than or equal to c.
Because c plus 1 is not inside of s.
Right. C plus 1 is not inside, so C plus 1 is for sure an upper bound of S. K is an S, therefore K is less than C plus 1. Okay. Assume, by way of contradiction, that K is less than C. Because we're trying to show that it's greater than or equal to C. The opposite of that is less than C. Make sense? And we're going to show out this Lisi contradiction. Let's see. So assume that K is less than C. What does that give us? That gives us that K plus 1 is less than C plus 1. Which gives us K plus 1 is in S. Contradiction. Why is that a contradiction? What was K? K is our max element in S. What is S? The set of all integers less than C plus 1. So, if K is less than C, then K plus 1 is less than C plus 1. So K plus 1 is an integer less than C plus 1. Therefore, K plus 1 is in S. But wait a second. K is the biggest element in S. Therefore, K plus 1 can't be in S. Contradiction. You follow the contradiction? Okay. So that means therefore there exists K in Z such that K is in C close bracket C comma C plus 1. Now we need to show that there's only one integer in there. And then we're done. Right? So 8. Now assume, by way of contradiction, that there exists some K prime element in Z, some K prime element in Z, such that K prime is also in C to C plus 1, where K is not equal to K prime. So assume that there's some other integer in C to C plus 1 besides just K, is what we're saying there. Alright? And we're going to show that this means that K minus K plus 1 is an integer between 0 and 1. That's going to be our contradiction. So, then we have that C is less than or equal to K prime is less than K is less than C plus 1. Make sure you understand all this. So we know both K and K prime are between C and C plus 1, right? That's what it means for them to be in the interval. But remember that K was our max integer in there, therefore K prime has to be less than it.
Right.
Which it is.
Which it is. Alright? So, in other words, let's see if you can follow this piece of logic here. Therefore, K minus K prime is less than C plus 1 minus C. Let me give you intuition for that real quick. Draw somewhere you can see on camera. Here's C plus 1. We know that K is somewhere in here, right? Here's K prime. Our picture looks something like that. Therefore, this distance is bigger than this distance, is what this is saying.
Yeah.
That's all that we're saying right there, right? And I'm going to add something onto here. And this is greater than 0 because K is bigger than K prime. This distance can't be 0. So the distance between K and K prime is bigger than 0, but it's less than the distance between C plus 1 and C. Which is the same thing as 0 is less than K minus K prime is less than 1. Which is the same thing as K minus K prime is in the interval 0, 1.
Right.
Which we know isn't possible.
Right.
There's no integer in there. Therefore, there's one and only one. Good?
Yeah.
Alright, let's see if we can get through the next two proofs real quick, and we'll be done. The next two are much simpler, so. Of course, there's an intuitive part to the first part, so we'll see. Alright, so next we're going to prove that the rationals are dense in R. Q is dense in R. How do we prove that? We prove for any open interval you have, there's always a rational in there. So, let A comma B be an open interval. So this is all the numbers between A and B. We're going to prove that one of those numbers is a rational. So there's a rational in there. So it doesn't matter how close A and B are together, we're guaranteed that there's always a rational between them. In other words, is what we're proving. You follow the thinking there? Okay. And then, let's see. Now, chalk. It's so hard to find good pieces that actually write. Is this for chalk? Need one. That feels right. Okay. 2, yeah. Let's see. By the Archimedean principle, there exists n in n such that 1 over n is less than b minus a. So let's do our picture real quick of what we're doing. Picture, here's A, here's B, and we're talking about all the points between them. So this distance is b minus a, right? So the whole idea is I'm going to find a natural number, 1 over n. And how big is that number? However big it is, I want it to be smaller than this interval. So if this interval is 2, then n might be 1. If this interval is 1, then n might be 2, so that the whole thing's 1/2. So n is going to make so that b minus 1 over n is between these. So b minus 1 over n is going to be a number between a and b, is the way I'm defining 1 over n. Okay? And then the way that we're going to think about this is now we're going to scale this picture up so that this is an, this is b, and we're going to multiply everything by n, and then this is b minus 1, since we multiplied everything by n.
Okay.
Or sorry, this is bn minus 1. You see that that's taking everything here and scaling it up by n.
Mm-hmm.
Now, I'm guaranteed that bn to b, bn minus 1 to b contains an integer. When we do close, open like that, I'm guaranteed that there's some integer in here, call it m, which means when we scale back down, m over n is guaranteed to be in here, which is irrational. And since m over n is in here, it's definitely between a and b. That's the picture of what we're going to do. So let's do it. So let A, B be some open interval. By the Archimedean property, there exists n such that n is less than b minus a, 3, then a is less than b minus 1 over n is less than b. Make sure you understand that.
Where did you just pull 1 over n from?
So b minus a is some number. It's the distance between b and a. And remember, if b and a are really, really close together, b minus a is a really small number. But by our corollary to the Archimedean property, for any small number you have, I can always find an n such that 1 over n is smaller.
So right there.
Yeah.
Okay.
So 1 over n is smaller than this. You could rewrite that as a is less than b minus 1 over n is less than b.
Right.
Okay. Then, looking at this part of the inequality, multiply both sides of this part of the inequality by n, then b times n minus 1, that's multiplying this half by n, is less than b n. 5. Then, there exists some m in z such that m is in b minus n minus, or b times n minus 1 to b n, like that, which is the same thing as saying that b times n minus 1 is less than or equal to m is less than b times n.
I have a question. Why isn't that closed brackets on both sides?
Our proof was like this. I'm using this proof. This proof says for any real number you pick, I can find an integer in this interval. So, bn is a real number. Therefore, in this interval, I'm guaranteed that there's an n, an integer.
I know that.
Oh, you're saying why didn't we do closed brackets when we proved this on both sides?
Not necessarily more to this one. Because bn, it seems like it's a set number. That's the whole set.
Right, so I'm saying that there is some integer. So I have bn minus 1 is less than bn. And all I'm saying is that there's some m between these. And I was just showing it this way real quick so you understand I'm using this proof. Does that make sense? This proof says pick a real number. Then from that real number to that real number plus 1, I'm guaranteed that there's an integer. Okay, pick a real number, b minus n. Then I'm guaranteed that from that real number to that number plus 1, there's going to be an integer in there, call it m. Make sense? So, m is between bn minus 1 and bn. Divide both sides by n. Then, or not both sides, but all three sides. Then, bn divided by n is just n, or sorry, is b. Negative 1 divided by n is negative 1 over n is less than. M divided by n is m over n is less than. bn divided by n is b. So m over n is between, let me write that cleaner, b minus 1 over n and b, which gives us that a is less than m over n is less than b. Because b minus 1 over n is bigger than a. So if m over n is bigger than b minus n, it's definitely bigger than a. So we found a rational number between a and b.
Didn't you really find one up there? B minus 1 over n? Isn't that a rational number?
No. This could have been pi.
Oh,
So this could be pi minus 1 over n, which is not rational.
right.
Good? And unfortunately, we couldn't get to showing that the irrationals are dense in R, but it's just a corollary of this. It almost immediately follows.
How? How hard
So-
is it to show that?
It's a 3-liner.
So why not just do it?
You guys don't mind staying a little bit late, then I'll do it real quick. You can leave if you want. I'll prove it real quick, and then it will be on the video when I upload it if you just want to watch it later. So, proof irrationals are dense in R. Let A, B, be an open interval, and now we need to show that it contains. Now we need to show that this contains an irrational number. Well, I don't need to do let. We just say then, let's see, divided by, then there exists some rational m over n in Q such that, we don't need to do m over n, we'll just say little q. There exists some rational number such that Q is in a over the square root of 2, b over the square root of 2.
And that can be any irrational number, right?
This is an interval. I'm guaranteed between, on any interval, here's one, there's a rational in there. So since Q's in here, that's the same thing as, we'll write down here, that gives me that, let's write it out explicitly, a over the square root of 2 is less than Q is less than b over the square root of 2, right?
Right.
Which, multiply everything by the square root of 2, gives me a is less than Q times the square root of 2 is less than b. There's an irrational between a and b. We can do a proof real quick that rational times a irrational is irrational. That's real easy to do. Let's have a rational. Let's say that a over b is irrational and times it by I to stand for irrational. And let's prove that this is irrational. Assume by way of contradiction that this is rational. Let's assume that there's some rational number that it can equal, right?
Yeah.
Well, what does that imply? That implies that I is equal to n times b over a times n, making it rational. An integer times an integer is an integer, integer times an integer is an integer, integer over an integer, that makes it rational. So an irrational times a rational is always irrational. Q was rational, square root of 2 irrational, their product is irrational. We found an irrational between a and b. Now I'm assuming you know square root of 2 is irrational, but we could have said let something be an irrational number. I just picked square root of 2 to save time. So yeah, we'll cover the next stuff next time, and then I guess we'll just, after we do that, we'll move on to the next chapter, cover as much material as we can, and then the following week we'll do the test. So next week, no test, but we will move on in the material to the next chapter, and then we'll go back and do the test.